Hi there. In this video we're going to look at another differentiation rule, and what we've been looking at in the prior videos is all these different differentiation rules. And if this is the first time you've seen it, this might seem a little bit overpowering to you. I apologize for that, but for better explanations on all these you can go back and look at the previous videos and the examples that go along with them. In the very last video we looked at the product rule, and I just want to make one clarification from that video. I think in that video I said f prime g plus g prime f, and that will certainly work. It worked in our example. It gave us the right derivative. But I need to tell you that the actual product rule is this thing here in blue. Okay, and really this top one and this bottom one are variations of that. I've just kind of used the commutative property of multiplication and addition to kind of rewrite it, and we could do that for this course. That the commutative property is going to hold true for everything that we're going to encounter. But you need to know that if you get into some higher mathematics, there are going to be some objects that you may encounter where those properties don't hold, and if you're trying to calculate the derivative of a product, you would have to use the one in the middle. Okay, but for this course, for this problem that we're going to do, any one of these formulas work. I'm going to highlight the bottom one, and I'm going to try to remember my product rule this way. Okay, if you learned it a different way, that's fine. I learn it this way because it helps me remember my quotient rule. Okay, so let's get into what is the quotient rule. The quotient rule is if I have a function that's a quotient of two other functions. And you can see that the pattern here in the numerator is identical to the product rule if I write the product rule this way. Okay, gf prime plus fg prime, gf prime minus fg prime. So there's one big difference: is product rule is addition, quotient rule is subtraction, and then in the quotient rule we're dividing by this guy squared. Obviously g of x can't equal 0. But that is your quotient rule. So let's do a couple of examples here and see if we can't apply the quotient rule. So our first function will be the following. Let's use 5x minus 1 over x squared plus 3. Okay, so how would we find this guy's derivative? Well, the quotient rule says take my denominator and just write it down. So I get x squared plus, whoops, not 1, x squared plus 3. Okay, then we're going to multiply by the derivative of my numerator. Well, what's the derivative of 5x minus 1? It's just 5. Okay, minus. Now, anytime I write minus and something's going to be written behind it, and I have minus this object right here, I always like to use parentheses just so that I don't make any arithmetic mistakes. Okay, so f. What is f? F is my numerator. I just simply write him down, and I'm going to multiply by the derivative of my denominator, which is 2x. And this is all over my denominator squared. Ooh, yeah, squared. There we go. Okay, so there you have it. I mean, really the only thing, all the calculus is done. The only thing left to do would be to simplify this. You could distribute this 5 through, maybe combine some like terms up top, and I think I'll leave that for you to do. We won't take the time on this video to do that. Okay, the next function is going to be a little bit more difficult, not much. But let's say we have the following. Let's say we have 3 minus 1 over x over what? Where did my example go? X plus 5. Okay, this is an x right here. Okay, so how would you go about doing this? Well, one thing you notice is not only do we have the quotient of two functions, but in one of my functions I have another quotient. And you might be tempted to think that when we go to find the derivative of the numerator, okay, in right here, this is the derivative of the numerator, that we really have another quotient to deal with. So that would be like the quotient rule inside of the quotient rule, and that just does not seem like a very fun thing to do. So what I like to do anytime I calculate a derivative of any function, I try to see if I can rewrite it so that it's a little bit simpler. And if I multiply the top and the bottom by x, notice that this is just 1 in disguise. It's really 1. So I'm not changing the value of this. If I multiply this function by x over x, turns out I get a much nicer function to work with. Well, 3 times x is 3x, and x times 1 over x is just 1. That looks like a much better numerator. And then down below I get x squared plus 5. Okay, so now this function looks a whole lot like this function up here. In fact, they even have the same numbers in them. They're just kind of mixed around a little bit. Okay, so let's go ahead and apply our quotient rule to f. And what does this tell me to do? My quotient rule says take your denominator and just write it down. X squared plus 5 multiplied by the derivative of your numerator. And the derivative of your numerator is just 3. Minus, and I always use parentheses for this next part, minus my top function, which in this case is 3x minus 1, multiplied by the derivative of the denominator. And the derivative of the denominator is 2x. And this will all be over x squared plus 5 squared. Okay, I think I got a different color on that. That should have been a little bit brighter yellow. That's better. Not really. Okay, so there you have it. So we're in the same position that we were in up here. This is your derivative, and like I said, you probably want to simplify something like this. This isn't too hard to simplify, but you do have to be careful. Sometimes you can go a little bit too far and make some careless mistakes. So once it becomes just a little bit simpler, I usually stop and call it good. So there is our derivative using the quotient rule. I hope that made sense to you. In the next video, we're going to be looking at a very powerful rule that's going to really expand the universe for the universe of functions that we can take derivatives of. We'll see you around.